Okay, so in this video, we'll be going over problems 21 to 25 of this year's AMC 10B. So starting with problem 21, each of the 9 squares in a 3x3 grid is to be colored red, blue, or yellow in such a way that each red square shares an edge with at least one blue square, each blue shares an edge with at least one yellow, and each yellow shares an edge with at least one red. Colorings that can be obtained from one another by rotations or reflections are to be considered the same. How many different colorings are possible? So we can draw our 3x3 grid right now. So we have 3 and 3. And we see that for our center square, we can choose any of the 3 colors to be in the center. So we have 3 right now, and without loss of generality, we have red. And then we know that red must border with a blue square, and so that means that we would have in one of these 4 squares at least one blue. And because colorings, we're not counting rotations, we can just put a blue in this square because we can just rotate the grid counterclockwise or clockwise to get the other positions. And so after we have the blue there, we would put a yellow either on top or at the bottom. And once again, it doesn't matter where because we could get the same graph by reflecting. And so we put the yellow over here. And now we know that the yellow must share an edge with the red, which means that here must be red. And then red must share an edge with the blue, so here we have to have blue. And then blue has to share an edge with yellow, and so this is yellow. And now we have fixed our top 2 rows. And so for the bottom row, we can do casework on the middle square. And so case 1 would be if we have another blue over here. And you see that that isn't possible, right? Because you know that a blue square must share an edge with a yellow square. And so if we put a yellow square over here, then that yellow doesn't share an edge with a red. And if we put it here, then that yellow also doesn't share an edge with a red. So the bottom square cannot be blue. And then if it's either red or yellow, if we assume that that's red, then there are 2 ways to color in the rest. So we would have blue over here, obviously, because red has to be next to a blue and yellow has to be next to a blue. And then over here we would have either red or yellow. And so that's 2 ways for if this is red. And then we can erase that, and then the next case is when the center is yellow. And once again, there are 2 ways. So yellow must, blue must share an edge with a yellow square. And so we would have over here blue. And then we would have red or blue over here. Because yellow doesn't work, because yellow has to share an edge with a red, and there's no more red. So that's also 2 more ways to color in the last row. And so over here we would have 3 times 4, which is 12 different colorings. And you see that none of these are attainable from rotations or reflections off another, because we've already considered that when we fixed the blue and the yellow. So that's question 21. For question 22, a 7-digit positive integer is chosen at random. What is the probability that the number is divisible by 11, given that the sum of its digits is 61? So we see that we have 7 digits, so 1, 2, 3, 4, 5, 6, 7. And the sum of its digits is 61, which means that there's so the maximum possible digit sum of a 7-digit positive integer would be when all 7 digits are 9, and that would be 63. And so we would have 9, 9, 9, 9, 9, 9, 9. And then we're essentially we have 2 minus 1s that we have to distribute within these 9 integers, or 7 integers, sorry. And so there's 28 ways to distribute these minus 1s, because you could either choose 2 of these 7 to give a 1, or you could choose 1 of the 7 to give a 2, or minus 1, minus 2. and so the denominator would be 28. And on the numerator, we would want the number to be divisible by 11. And so essentially we see that, divisibility rules for 11 are this plus this plus this plus this minus this minus this minus this. The number that you get would be a multiple of 11. And so right now the digit, like the number that we get when we do this is 9. And if we want it to be 11, then that means that we would have to distribute the minus ones over here, and over here to make that 11, because it would be 9 minus 2, which is 11. And so we see that there's 6 ways to do this, right? Because either you could give both the negative ones to one of these, which gives you 3, or you could give 1 to 2, which also gives you 3. And so you get 6 over 28, which is 3 over 14, which is A. Okay. Problem 23. So a rectangular grid of squares has 141 rows and 91 columns. Each square has room for 2 numbers. Horace and Vera each fill in the grid by putting the numbers from 1 to 141 times 91 into the squares. So Horace fills the grid horizontally. He puts 1 through 91 in order from left to right into row 1, and he just continues that, and Vera fills it vertically. How many squares get 2 copies of the same number? So let's say that we have X and Y. So X represents the column and Y represents the row. And so these represent the squares where we have 2 copies of the same number. And so Horace's number would be 91 times Y minus 1 plus X. And Vera's number would be 141 times X minus 1 plus Y. And so we would equate these, and these two are equal. So what this gives us is that 140x minus 9y is equal to 50. And we can divide both sides by 10 to get 14x minus 9y is equal to 5. And now we can solve this, right? So essentially, the general term would be x y is equal to 9k plus 1 and 14k plus 1. Right, because those are the values that satisfy our equation, because the GCD of 14 and 9 is 1. And we see that if x and y is equal to 1, then that satisfies the equation. So we evaluate this for k, and we know that since 1 is less than or equal to x is less than or equal to 91, and 1 is less than or equal to y is less than or equal to 141. We see that both of these give 0 is less than or equal to k is less than or equal to 10. And so there are 11 possible values for k. And so we have 11, which is C. Okay, question 24 says a frog hops along the number line according to the following rules. So number 1, it starts at 0. If it is at 0, then it moves to 1 with probability 1/2, and it disappears with probability 1/2. And for all of the other numbers, 1, 2, and 3, if it is at n, then it moves to n plus 1 with probability 1/4. It moves to n minus 1 with probability 1/4, and it disappears with probability 1/2. So what is the probability that the frog reaches 4? So we can come up with like a recurrence equation for this. So P4 would be equal to 1 because it's at 4 already. And then for all of the other ones, P0 would be 1/2 P1 because it can only get to 0 from 1. P1 is equal to 1/4 P0 plus P2 because it can get to P1 from P0 or P2, both with a 1/4 probability. P2 would be 1/4 P1 plus P3. and P3 would be 1/4 P4 plus P2, which is also equal to 1 plus P2 because we have that P4 is equal to 1. And then we can solve this system. So we have P0 is equal to 1/2 of P1, and so that means that P1 is equal to 1/4 of P0, which is 1/2 of P1. And then plus P2. And then we can solve for P2. So we can multiply both sides by 8. So 8P1 is equal to P1 plus 2P2. And so P2 is equal to 7 over 2P1. And now we use the same thing in this equation. So P2 is equal to 1/4 times P1 plus P3. I guess we can substitute we can multiply both sides by 4 first. So 4P2 is equal to P1 plus P3. And then 4P2 would be equal to 14P1. And so this is equal to P1 plus P3. And so 13P1 is equal to P3. And finally, for the last equation, we have 4 times P3 is equal to 1 plus P2. And 4 times P3 is 52P1 is equal to 1 plus P2, and P2 is 7 over 2P1. So if we isolate for P, we get that 97 over 2P1 is equal to 1, and so P1 is equal to 2 over 97. And then we can substitute everything. So we have P0 is equal to 1/2 of P1, so P0 is equal to 1 over 97. And so the probability that the frog reaches 4 would be this, which is 1 over 97. Okay, question 25 says square ABCD has sides of length 4, points P and Q lie on AD and CD so that AP is 8 over 5 and DQ is 10 over 3. A path begins along this segment from P to Q and continues by reflecting against the sides of ABCD. If the path hits a vertex of the square, it terminates there, and otherwise it continues forever. At which vertex does the path terminate? So over here you can see I've kind of put the square onto the coordinate axis or coordinate plane, but we can ignore that for now. And let's draw like a smaller version of the square on this side. So this is A, B, C, and D. And we have our line that looks something like this. And so kind of what we do for this problem is you see that you can make the line from P to Q that bounces around, like you can make it a straight line by reflecting this square, right? So for example, if we reflected this over this way, then we see that what used to be this would become this. And so now the points this, and this are all a straight line. And we see that is because we have this angle is equal to this angle is equal to that angle. And so they're vertical angles, and so they're collinear. And you do the same thing for the rest, right? You can reflect this over, and then you would have this line continuing over there. And essentially, now PQ becomes a straight line, and we want to see whether or not it intersects a point where the x-coordinate and the y-coordinate are both multiples of 4. And so first you can find the formula or equation of the line PQ. And so if we scroll back up, we have that AP is 8 over 5, and so P is 0, 8 over 5. And we have that DQ is 10 over 3, and so the Q would be 10 over 3, 4. And so the equation of the line would be y is equal to, let's write it over here. So y is equal to the slope, which is 4 minus 8 over 5 over 10 over 3, which is 12 over 5 over 10 over 3, which is something like 18 over like 25 x, and then the y-intercept is 0, 8 over 5, so plus 8 over 5. And then we can multiply both sides by 25 to see that 25y minus 18x is equal to 40. And we want this to have a solution where both y and x are multiples of 4. And we see that we do have a solution, which is that x is equal to 20 and y is equal to 16. And yeah, that's our smallest solution, because we can just test out smaller values, I guess, and see that nothing else works. And then essentially we extend this thing that I drew over here to become a 5 by 4 grid. And so it would be like something like that. And then we just draw our line so that it touches this and it starts over here and it looks like that, something like that. But it never intersects any of these points, so my diagram is kind of off. So the first intersection that it intersects is over here, and we just count reflections, and so we have this is equal to point P, so you can just start reflecting. So B is over here, B is over here, B is over here, and B is over here, and then B is over here, right? And so our final point where the path ends would be at vertex B, and so our answer is B.